Hello, my name is Ben Jambor. This is the recorded lecture for the class project of CE 562. My lecture will be on Chapter 13, but more specifically, this lecture is going to cover the design of component supports for seismic forces. In class, we discussed Chapter 11, which introduces the parameters that are used in seismic design. And then we use those parameters in Chapter 12, which covers the requirements for building structures. But Chapter 12 only covers the requirements for building structures. It doesn't cover the consideration of the components within the structure. So what about them? They experience the same earthquake as the building does, and they need to be restrained. Well, they may need to be restrained from those seismic forces, and Chapter 13 does that. So the scope of the chapter, there are some limitations to whether or not Chapter 13 can be used. That the prime limitation is if the component in question, the weight of that component exceeds 25% of the effective seismic weight of the structure, then the component is no longer classified as a component. It's now classified as a non-building structure, and its design is according to Chapter 15. There are also some exceptions where we may not have to use this chapter. We can save some time on the design exemptions. Some of those exemptions are for furniture. Cubicle furniture is not required to be designed for seismic forces. Neither is temporary or movable equipment. And then the rest of these exceptions have to do with the seismic design category and the importance factor. The importance factor we'll talk a little bit more about later. The seismic design category is defined back in Chapter 11. It's the same seismic design category that the facility structure has. It's related to the short period response acceleration parameter. That's defined in Chapter 11. So our support needs to be designed for the forces generated from the seismic acceleration of the component. And we're given provisions in this chapter to do that. The first of which is section 13.3, where we're given an equation to determine the horizontal or lateral seismic force of a component. In this equation, you'll see some familiar parameters and some new parameters. The first you may notice is STS, that is the short period response acceleration parameter. That's the same as what we find in Chapter 11. That is a site-specific parameter, meaning it applies globally to the site, to the building structure, to the components, to non-building structures. It applies everywhere. We also have the response modification factor, which is similar to what is introduced in either Chapter 11 or 12 for buildings. However, new tables are provided in this chapter to determine it. The response modification factor is essentially the capability of the component to absorb energy. Building systems are typically much more ductile than components, so their RP values are much higher, and here we have generally much lower values tabulated. There is a new component importance factor, IP, introduced. This is not the seismic importance factor. The seismic importance factor is explicitly tied to the building risk category, where the component importance factor is not necessarily dependent on the building risk category. It is more of a question of how important is this component? What are the consequences of its failure, and does it need to continue in operation after a seismic event? So this is typically a judgment call from the engineer, though it can also be decided by the facility owner or the authority having jurisdiction. The values range from 1 to 1.5, where 1 is the component needs to stay in place, but during a seismic event, it could sustain heavy damage, and it doesn't have to be operable after the event. Where a factor of 1.5, the component must remain operational after a seismic event. Maybe it's carrying toxic materials, maybe it feeds functions for a risk category 4 facility, so it needs to remain operational during an event, or maybe its failure could result in the failure of an important component. That would earn a component a factor of 1.5 as well. We also have a new parameter given here, that is the component amplification factor, AP. This parameter, well, dynamic loads are more severe than a static load of the same magnitude. So this parameter is related to the component's sensitivity to dynamic load amplification. It is determined by testing like shake table tests. As a general rule, a more flexible component is more prone to dynamic amplification of load, or dynamic load amplification. We also have a parameter that, well, it's a modification for the component height in the facility. So a component high up in the facility will experience greater seismic accelerations than a component near the base level of the facility. The base level is pretty much synonymous with the ground level. So a basement that is below ground level is considered below the base level. It starts where the ground starts, and that's proved by a figure in the commentary. This figure here, where Z begins at the ground and everything below is considered under base level. And you can see in this figure, as you go up, the horizontal force increases with height, and it caps at the top of the structure. Okay. We have a minimum boundary that our acceleration, that our force as a result of acceleration can be, and we have an upper limit that our acceleration, the force due to our acceleration, does not have to exceed. That is the lateral force that the support will have to sustain. We can also determine a vertical force, and it's much easier. It's covered in section 13.3.1.2. It is a concurrent vertical force that either adds to or subtracts from the dead load. If the primary load case is checking uplift, then you would want this to subtract from the dead load. You would use this with the 0.9 load factor. Or if it's downward loads that you're considering, this would add to the 1.2 factor. There is one more important parameter in this chapter that's related to what we're doing, related to the design of these structural supports for non-structural components, and that is the seismic overstrength factor. And you use this overstrength factor whenever you are anchoring into a non-ductile surface such as concrete or masonry, right? So you have an interaction between steel and concrete. Either can fail. You check both. If the concrete fails, then that failure is brittle. It happens sudden. And the overstrength factor can account for that brittle failure. So you either are responsible to prove that the connection, that the anchorage does behave ductilely, or in lieu of doing that, and honestly the easier thing to do, is to just apply this overstrength factor to the seismic load combination. So this will increase, let's go to chapter 2 very fast. Whenever we have our seismic load combination, that overstrength factor would appear in front of this EV and EH, amplifying them by a prescribed amount that's presented in the tables of chapter 13. So we're going to do an example, and we're going to use these equations, and we're going to determine some forces. So we have a electrical panel here. This panel weighs 140 pounds. It is attached to this cantilever post. There are 2 posts. At the base of the post is a base plate with 4 anchors. A lateral force on this panel, let's say acting in this direction, or this direction, is going to incur a moment at the base of the post, which is going to be resisted by these anchors. So you need to determine a flexural force in this member. This is a strut member, if you can't, whatever. Not important. What's important to this problem are these anchors, because that moment at the base will be resolved into a force couple, where these 2 anchors on this side, assuming the force acts this way, will be in compression, and these 2 anchors on this side will be in tension. So in this example, we are going to determine the horizontal force due to seismic acceleration of the panel, the vertical force due to seismic acceleration of the panel, and the tension in the anchor group at one of the post bases. What we know is that this panel is anchored at the base floor level. This is a risk category 2 facility, and this panel is not required to function after an earthquake, and it's not near any critical systems. The panel weighs 140 pounds, and our short period response acceleration parameter is 0.49. So, and also our total structure height is 14 feet. The first thing we might want to do is see if any of the exemptions of chapter 13 apply, because if we can save time in the design effort, that's saving us money. So if we don't have to design it, then let's not. So let's see. We need to determine the seismic design category. That is in chapter 11. We are going to go to page, let's see. Well, I think it's 140. Let's find out. It is. So table 11.6-1, we can determine the seismic design category based on our SDS. We had 0.49. That puts us at this level. Risk category 2, we have a seismic design category C facility. So let's write that down. Let's say that we have seismic design category C. And before, the next thing we need to know before determining if this panel is exempt from seismic design criteria is we need to know the importance factor. This panel is not that important. It's not required to function after the earthquake, and so we are going to assign it an importance factor of 1.0. Let's go back to chapter 13 and scroll, don't have to scroll anywhere, they're right here. We will go to mechanical and electrical components in seismic design category C. They are exempt so long as the component importance factor is equal to 1.0. So this panel is technically exempt. We would not have to use this chapter to determine the seismic load. We would only have to design the supports for gravity loads and maybe wind loads if it's exterior to the facility. However, for the sake of this example, we are going to determine those loads anyway. So let's go back to our example. Let's begin filling out equation 13.3-1. Let's go down to it. We need the component amplification factor and the response modification factor. Those are provided to us in the same table. There are two tables, two noteworthy tables. The first of those are coefficients for architectural components, and here you can find things like partition walls, drop ceilings, laboratory equipment. That's not what we're looking for. We're looking for electrical components, so we're going to keep scrolling to the seismic coefficients for mechanical and electrical components, and we will find our case. So we have a panel. That panel is going to be made of sheet metal. So we have, let's see, here, other components constructed of sheet metal framing. So we do have panel boards up higher somewhere in this, but this isn't really a panel board. This is a panel containing something. I don't know. But we're going to call it another component constructed of sheet metal framing. So our amplification factor is 2.5. Sheet metal framing is highly deformable, so we're going to have a higher amplification factor, the highest that this table provides, actually. But that's going to absorb energy pretty well. So we have also a higher response modification factor of 6. And for future note, we're just going to record that we have an overstrength omega factor of 2. So let's tab over and type up those parameters. We have an AP of 2.5, an RP of 6, and an omega value, let's see, omega naught of 2. Okay? So we have most of these parameters. We do need to define the height in the structure at the point of attachment. Note that it's at the point of attachment to the structure. It's not necessarily the height of the component itself. So even though our component is 72 inches off the ground, our attachment is at the base level. So our Z in this case, and I believe we're going to have to go to a new sheet, our Z is equal to 0. 0 feet. And with that, we have all the parameters we need. So I am going to quickly take a grab of this just for my reference. I'm going to slap it here. And we're going to build this equation. So FP, we're going to say FP calc, will be equal to 0.4 times AP times SDS times the weight of our component. It's 140 pounds. And that's going to be divided by RP divided further by our component, or our importance factor. And then that whole quantity will be multiplied by the height modification factor. It's Z over H. So our worksheet has defaulted to newtons. Let's fix that. We will have a design force, a force of 11 pounds, laterally acting on this support, on the two combined supports. But we're not finished. We need to check the minimum. So the minimum is going to be 0.3 times SDS times the importance factor. Let's define that. We're going to have FP minimum, which is 0.3 times SDS times IP times our weight, which is 20.5 pounds. So our minimum exceeds our calculated value. We can already guess that our maximum doesn't matter here, but I'm going to calculate it anyway. So FP maximum is 1.6 times the same. So we'll copy this over and change this scalar to 1.6. So the maximum force that we would ever need to design this component for at any facility with any SDS would be, that's an incorrect statement, forgive me. The maximum force that we would have to use potentially for this support is 110 or so pounds. We're going to use FP Calc in our calculations further below. So that's our horizontal force acting on the panel laterally. We now need to determine the vertical force, and that one's easy. So let's do, what do they call it? They don't call it anything. We're just going to call it EV. Now you can determine the vertical force outright by using the equation that they provide. Times SDS. So we would need to consider a vertical force of 13.7 pounds, or you can use this 0.2 SDS to modify the dead load factor, because in both cases, whether it's the dead load factor or this 0.2 times SDS, it gets applied to the weight anyway. So if you were checking a uplift case or a minimum dead load case, you could simply have the quantity of 0.9 minus 0.2 times SDS. Your new dead load factor would be 0.8. Similarly, you can do this for a maximum dead load case of 1.2 and have a factor with adding 2. Have a factor of 1.3. So instead of calculating this outright, you could just handle it in the load combination. So now we are going to, I misspoke earlier, we're going to use FP min for our support design. We're not going to use FP calc because FP min controls over it. Now we are going to determine tension in the anchors, including the effects of seismic overstrength. So our moment arm from the centroid of the panel to the base is going to be 72 inches. So let's have moment at the base be 72 inches times our FP min joules for a moment of, let's do that in pound inches. No, let's do that in kip inches. 1.5 kip inches. If you remember from statics, the simple way of, there's more math you can do, but the simple way of resolving a moment into a force couple is just taking the moment between the forces between these anchors and dividing it by the anchor spacing. So to determine our tension in the anchor, we are going to have the moment at the base divided by the spacing of our anchors, 6 inches. But that needs to be increased by our overstrength factor, omega naught. We're going to apply that at the front. So the anchor group, and then we also have 2 posts, so we are going to divide that by 2. So the anchor group at the base of a single post, these two tension anchors would need to collectively resist a tensile load of 247 pounds. You can, quickly, you can also just determine the shear demand. So if we have effectively 8 anchors resisting shear, we can take our demand force, we'll call this V_anch, increase it by the overstrength factor, take our demand force and divide it by the number of anchors that we have. Each individual anchor would have to resist 5 pounds of shear. However, since these anchors are going to behave as a group, we're going to divide it by the number of tension groups we have. So actually each anchor group will need to resist 10 pounds of shear. So not very much in this component, but it could be a whole lot more in other situations for different importance factors, for different sites with higher seismic parameters, for different heights of the structure and different weights of the components. You could have a significant seismic force to deal with in your support, and you are going to experience that in the homework. That's all for today's lecture. Thank you.